All right, guys. This video is basically a walkthrough of the default CUDA Toolkit 9 program that you get with downloading the CUDA Toolkit 9.0 programming environment, right? So I am on a Windows machine running Visual Studio Community 2017, running CUDA Toolkit 9. I have a GTX 1080 Ti graphics card that I am using to run all my CUDA code, right? Now, if you haven't gotten to this point yet, where you actually have Visual Studio and the CUDA Toolkit 9.0 set up, you could check my other video on the CUDA Education YouTube channel and get up to speed. It basically explains everything, right? So this video is walking you through pretty much the code that comes by default with the CUDA Toolkit 9, and we're going to go step by step through all the things that I know about why and how this program runs. Now, a couple of background things. Number one, I'm learning this stuff relatively new myself. I am not even pretty much a C++ programmer or C programmer. I come from a web programming background, so you're talking PHP, JavaScript, Cold Fusion, web programming stuff. So I'm learning it and I'm teaching you, and I think it's a good way to go because I basically don't assume anything. And for all those who are trying to learn CUDA and understand how to program it, and it's basically the future. I mean, artificial intelligence, autonomous driving, all that stuff is going to be programmed through the CUDA, the NVIDIA graphics chips which run CUDA. This is the C++ implementation, of course, as I suggested. Now, if you want to get into the CUDA, if you wanted to run or get the default program, just in case you want to get back up to speed, all you do, you open up Visual Studio, you go new project, CUDA 9.0, CUDA 9.0 runtime, then you do tutorial. I'm going to do 3 this time because I screwed up the video on the second one, so it's really well, anyway. So then you just leave everything else, you do okay, and then your default program comes up, right? As you can see here, this is the default program that comes with CUDA Toolkit 9. At this point, they might be on CUDA Toolkit 9.1. I doubt they actually changed the default program. I tried running CUDA Toolkit 9.1, but I couldn't install it successfully, so boom, we're back to, I'm sticking with 9.0. Now remember, when you create a new project, you have to go to the properties and change the compiler to 2015. It's something they haven't, they forgot to, whatever, but it would only run with the 2015 compiler. So just to make sure we're all on the same page, I'm going to build this thing and make sure that it actually runs. And yeah, rebuild successful, start without debugging. So basically we have 2 arrays, 1, 2, 3, 4, 5, and another one, 10, 20, 30, 40, 50, and we add them together to get the result, right? Now this arithmetic and result is all being generated with the GPU, with the graphics card, okay? Now, a little bit about vocabulary. First of all, when I say host, I'm talking about the CPU on your computer. So the CPU is like the Intel i4 or i5 or i7 or 6, whatever it is, but it's the Intel chip that sort of runs everything on your computer under normal circumstances. So you're browsing the web, maybe you're in Word or Excel or whatever, it's all the CPU, right? When I'd say device, or I say GPU, or I say yeah, or I say the kernel or anything like that, I'm talking about GPU stuff. I'm talking about the graphics card, the device, graphics card, whatever that comes with your computer, or should come with your computer if you're able to install and run this stuff. So um, there are two different devices that is being touched by this code right here. Now I'll give you a little bit of a surprise. The majority of the code that you see here, the majority of the code is being run on the CPU, right? Or it's being run on the host. It's not being run on the GPU. It's not being run on the device. So to give you some context, what's happening is that the host is in charge of housekeeping. So think of it as if let's see. Think of it as you're preparing the environment in order to make the GPU dance or run, right? Or think of it, you're preparing the stage for the performer or the celebrity or the musician or the artist to come on stage. But before they can come on stage, you have to prepare the stage. You have to build a platform. You have to put on install the lights, install the stereo system and everything, right? So the CPU or the host is in charge of preparing everything so that the GPU can do its thing. The purpose of the GPU, the purpose of CUDA, the reason why we even think about doing this stuff is one simple thing. It's speed. It's speed. What a GPU can do in 100, what a CPU can do in 100 seconds, the GPU could probably do in a nanosecond, right? I mean, it's like absolutely on a different scale. And it does that because it's parallel computing. It's doing 1,000 different things all at once. It's simultaneous, it's parallel. On the CPU, on the host side, you can only do one thing at a time. So it's sort of sequentially, right? This, then that, then that, then that, then that. You can't do this before you do this. You have to do this first, then when it's done, you do this, then when it's done, you do this. On the GPU processing, everything is being done. Like, let's say you had 5 lines coming down here. Everything is being done simultaneously, right? And that's the beauty of the GPU. It's because of this speed enhancement why autonomous driving, why artificial intelligence is possible, because you have to do a lot of processing, a lot of data crunching, a lot of decisions have to be made in a split of a second, right? And you can't do the stuff if you're taking forever to process or to make a decision. So this is why CUDA exists. This is why we're here. nVidia is making billions and billions of dollars simply because of this technology, right? And this is sort of your introduction. So we have the host stuff and we have the GPU stuff. And we have to make the two of them dance. The host is preparing the stage, is preparing the soil, sort of like in horticulture. And when you're planting a plant, you have to prepare the soil. And then the kernel or the GPU is the plant that you put into the soil, right? But of course, it has to be, the soil has to be prepared first. All right. What else? Is there anything else? No, I think we could start. So I'll just run through, I'll basically just run through from here to here, and then from here we'll follow what the program says. So all of these are just libraries that come by default with the toolkit. Don't really have to worry about that. Now here you have this CUDA error _T. Now there isn't much information about it, but from what on the nVidia website and everything, it basically is a data type or a definition where it takes an error that is generated off of the GPU, off of the device, and it creates a string representation of the error so that we humans can actually understand what the error is saying. So if the data, if there's an error that's returned that there is no string for it or it doesn't really recognize it, it would just say unrecognizable error has occurred. So as far as I know about this thing right here. And then you have this add with CUDA function that actually is part of the whole preparation of pushing everything to the GPU, to the device, so that it could do the arithmetic and generate the results. So this function is mentioned here. It's mentioned in other places, but for some reason they decide to make it the first thing they mention in the file, right? And it takes an integer that's C, and notice it has this asterisk here. Now, for those that are not C++ or you know, aficionados and what have you, the asterisk just basically means we're dealing with the value at C, not the memory address or the memory at C, but the value at C. So it's saying, you know, give me, you know, this represents the value at C or whatever is passed to it. This is the value, constant integer A, the value at A that's passed to it, the value at B that's passed to it. And then we have this unsigned int size, and that is just from experience with this code, it's sort of a constant. I'm not gonna get into details about what all this, but just understand you have this CUDA T thing that's error checking. You have the add with CUDA function that's declared with all these parameters. So we pass values into the function and then the function does something. Okay, next order of business. We have a global function, right? Now, what does global mean? Global basically means that it's a function that can be called from, right? So global means that both the device or the GPU and the host, the CPU, can call this function. Then it does void, add kernel, and again, it's taking the value, or it's saying, you know, the value at C, value at A, value at B, and then it has parameters or things that it's passed to the function, and then it processes the bad boy. Now, understand that this function, let's see the result of it again. So basically it's this guy right here. So you see this C, you see this C equals blah, blah, blah. It's basically saying the value at A at 1, where it's equal to 1, and the value at B at 1, which is equal to 10. Add these two together and give me C, which is the 11 right here. So you can see 11, 22, 23, 33, 44, 55, right? That's all that's doing. Now, got to pause here for a second. I have to pause. Pause and take a deep breath. Get rid of him. In a C++ implementation, this would have been done with a for loop, right? So you would have for I equals 1, then you would do the addition with I equals 1, then you do I equals 2, then you do, you know, then you get the value at 2, then you do I equals 3, and then it does it again, and then I equals 4, and it does it in a for loop. You notice here, in the kernel GPU implementation, it's just one thing that pretty much just runs one time. It's because we have these things called threads that in our instance, we created 5 of them, and all 5 threads hit this thing all at once, simultaneously in real time, not one after the other, right? So bang, and you get your results for C and you're done. It's not 1, 2, 3, 4, 5. It's bang, one time. So that's what this thread idx.x is. It's basically saying for each one of the threads, so you know, it might be thread 0, thread 1, thread 2, thread 3, and thread 4, which, you know, basically comes to 5 threads. You know, so I for the 1 is going to be 1 for the first thread, it's going to be 2 for the second thread, 3 for the first, and you'll generate the arrays in real time simultaneously for all 3 of them, right? That's what this is doing. This is done on the GPU, not the CPU. It's done on the device, not the host. And this is the magic that's happening right here. But anyway, this is just a declaration. You're declaring it. It's a global function. Both the host and the thing can call it. And that's all you need to know for now. Now, in C++ world, things start with main. All programs start with main, right? Main is where, you know, the program starts. So when you run the program, you basically go, the computer goes, okay, where is main? Main is here, so start from here. And this is where all the magic starts to happen. I really should have maybe just started explaining from here, but since this was already in our face, I just wanted to go over this. But anyway, so this is main, it starts, right? Now, remember I said that the host or the CPU or whatever else you want to call it does all the housekeeping. It prepares the soil, it prepares the stage, it sets up the environment for things to happen. So what is the CPU doing here? It's initializing variables. So there's a constant int variable called array size, and we're setting it to 5. Why 5? Because all these bad boys, all these arrays are size 5, right? Size 5, right? So we're saying array size is 5. Then we're doing, we're initializing the first A array, and it's 1, 2, 3, 4, 5. The second A array is 10, 20. So basically we're initializing these guys right here, right? So we're initializing them on the CPU side, on the host side, not on the GPU, not on the device, right? And then we're setting int C of array size 5, because they're all 5, right? Size 5. And I think this is just 5 zeros, but maybe I'm wrong because, you know, C++ is kind of different like that. But I think it's just 5 zeros, right? You could enlighten me in the comments below. Okay, so now, after you do that, we have this error checking thing again, CUDA error T, and it has this variable CUDA status that I think the program just always uses this variable CUDA status to manage all the errors. But anyway, so it has add vectors in parallel, CUDA error, CUDA status, and then add with CUDA C, right? So add with CUDA, and then it has all these things, right? So it's basically calling the add with CUDA function, which was mentioned up here, but not really defined. But we're not going to define it here. We're not going to move away from this thing. We're just understand that add with CUDA is called here. Then we do a whole bunch of error checking. CUDA status, if the CUDA status is not equal to CUDA success, which basically means the process didn't actually go through, print out to the user that add with CUDA failed and return 1, right? So this sort of is the heart of, or this is the journey that you start with to actually get to the kernel and run the thing and get a result and get it back or whatever. So by the time this thing is done, you already have done the arithmetic. You already know what C is, what the result is, right? You basically already have done the processing, right? By the time you're done, you reach here. So now what this is saying is print this, which is predefined. We didn't have to do any calculations for this. No big effort was expended to get this. But then you have your C here, which is the result, which is why we needed the graphics processor to do it, right? This guy. So that's your result. So this is the magic. So print out everything and say, okay, it all equals to this, right? Okay. After you do that, because we're basically done with the GPU at this point, well, reset the GPU. And if something happened with the GPU that it didn't reset successfully, tell us, and then be done with the program. And that's pretty much the main thing, that's the line of events, if you will, that are triggered in the entire program. Now, of course, once we take this branch and start messing with add with CUDA, then we get into a lot more stuff, right? Because there's a whole bunch of code and text down here, and I'm sure you're shaking in your boots and you're just absolutely nervous about what all that stuff is. But have no fear, CUDA Education is here. So once you call this, then we go to add with CUDA. Now, what do they say about add with CUDA? Add with CUDA, helper function for using CUDA to add vectors in parallel. Okay? So again, the function is mentioned here, and I'm not sure why they mentioned it here, but I think they had to declare it prematurely. But this is where it's all defined. So I don't need to go through C, A, B, unsigned int size. Notice how they didn't have to do the asterisk on this one. But remember, value, 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 asterisk, value, value, value. And then this I guess, is just a regular value, right? Now, folks, we're still on the host side. We haven't gotten to the brand new shiny GPU that you spent so much money to buy, and you wanna actually run it and have it do some whiz bang. We haven't actually gotten there yet. We're still on the CPU. Okay? So what do? We're doing housekeeping. So we create a whole new set of variables for the device, for the GPU. We call them dev A, dev B, and dev C. Notice how it's called dev, which means device, which means GPU. So it's similar to these guys here, right? So this was on the host, and I mean, this is, it's the device version variables for the device. But I mean, we're still, these are created on the host right now, but it's going to be used for the device, right? So host variables, device variables, right? Now you notice how you have the asterisk because we're talking value. So we say assign the value at dev underscore A to 0. Assign the value at dev underscore B to 0, dev underscore C to 0. Assign it to 0, okay? And then it does CUDA error underscore T CUDA status. Yeah, it's doing error checking again. This code is, but I guess they have to be because many people are running it with different setups, but it's all preoccupied with error checking. But anyway, so we create our CUDA status. We have our device variables set aside, initialized and set aside. We're still on the host though. We're still on the host. Still on the host. Before we go on, more housekeeping. We have to select which GPU we're actually going to use to do the arithmetic and all that whiz bang, right? So CUDA status equals CUDA set device 0. Now remember, you know, for me and you and all the normal people out there, we just have a simple setup where we just have one computer with one graphics card, and that's it. But you know, for the special ones out there, we use they have multiple GPUs on their system. Like especially if you're at a university and you're doing high performance simulation, or you're at a video game developer or whatever, and you have multiple GPUs. You could choose to do one or the other or both or whatever. But this CUDA set device, basically you're saying, you know, select this device, and if there's an error, tell them that there's an error in selecting the device, and do you have a CUDA enabled GPU? In the previous video about how to install CUDA Toolkit 9, I talk about CUDA enabled GPUs and what it means, and maybe you have to go out and get an nVidia card to get this going. But if you can't select the GPU, it gives you an error, right? Okay, fine, done with that. Now we have to go to allocating memory on the GPU for the variables. So let's pause for a minute. Okay. Before you could actually push variables or push information to the GPU or to the device, you have to actually allocate what I like to call buckets of memory space on the device, on the GPU. So it's sort of like before you could, you know, carry a whole a bag of sand over to the GPU, you actually have to create a bucket on the GPU with the correct amount of space or with the correct amount of bytes that can hold the sand. So you create the bucket of memory or the bucket of information, or the bucket or you allocate the memory before you actually push information to it. So CUDA status again, we're doing error checking, equals CUDA malloc. Now for the C++ folks, malloc means memory, right? So CUDA malloc, and then it does this void thing. Don't ask me what this does, but it does something. But notice here, you have an % dev underscore C. Remember we were using asterisk here? We're using % here. The reason why we're using an % is because we're not talking about values anymore. We're talking about memory. Memory. So we're saying CUDA malloc or allocate memory or the memory at address C, the amount of memory at address C. We want to do that. The memory for address C, the memory address for the variable C, I'm sorry. The memory address for variable C, we want to use the size. We want to basically allocate 5 integer variable memory space sizes for it. So in other words, let's say, for example, an integer takes up 1 byte, right? And we know that dev C is supposed to have 5 integers in them, right? So what we're saying is that assign 5 bytes, because it's 5 times the size of an integer, assign 5 bytes and allocate it for dev C, where the %, is like the memory address for dev C, right? And then we do error checking again. If you're not able to allocate it, then you tell us. We did that for dev C, we do that for dev A, and we do that for dev B. So it's all basically the same thing. You're allocating memory on the device for these guys, right? You have to do this before you actually push the variables over there to the device. So then now, once you dealt with the memory on the graphics processor, on the device, then you can start to copy the host variables over to the graphics processor, over to the device. So CUDA status again, but then we do CUDA mem copy. And what that does, it's just a memory operation. So you have the destination, which is dev A, and you have the host, or the source, sorry, destination, the source, which is A, and A came from, as everyone knows, A came from here, right here. This was where A came from. So push that over to the information over from A to dev A. And then notice here, we still have to mention the amount of memory that we're dealing with. How much memory is this operation dealing with? Notice it's the same size as this guy, right? So it's the same size. So we created the bucket, and we also have to re-mention it again that, hey, this bucket, has this amount, and that's how much this operation should take. And then we do the actual, we call the actual function that does the movement. So CUDA mem copy host to device. All right, so we're moving from the host to the device, and that makes sense because we have our host variables here, and we're moving it over to these guys here, which we already initialized and everything, but we're carrying them over now. Where is it? Sorry. We're carrying them over now to the device, host to device, right? So that's that. See? And then we're doing some error checking again. CUDA status not equal success. It failed. We do that for A, we do that for B, and that's it. We don't have to do it for C because C is just an empty thingamajig, right? Well, no, not here, but here. C was just empty. C is just a variable to hold the result. So we don't really know what C is yet. And that's why we're pushing these two variables over into the device so that they can do the thing, right? Do the addition and everything. Now we actually get into launching the kernel. So this part, this is all CPU host stuff. This, well, you know, we're actually pushing it over into the device here, but it's still being managed by the host, sort of, right? This right here is where we actually launch a lovely kernel on the GPU. So you finally get to use your brand new whiz-bang GPU processor. So block of 1 and size of 5, or threads, 5 threads. 1 block, 5 threads. Remember, size was initialized to 5 because up here it was being called with size, which is this guy right here. And remember, size is this guy right here, right? So we're doing 1 block, 5 threads. And we're passing in our device variables. So see, now we're passing the device variables into the kernel for add kernel, right? So when this happens, we're basically go all the way up to here and we do the operation. Now this bad boy is being performed on the GPU or the device, whichever one you want to call it. This is GPU stuff, okay? Now, I did this before, but it didn't record properly, so have to do it again. All right. So let's start down here. All right, so we're dealing with this bad boy. 1 block, 5 threads. What does that mean? 1 block, I'm like Picasso. Okay, 5 threads. 1, 2, 3, 4, 5. 1 block. This is the block right here. 5 threads. 1, 2, 3, 4, 5. Okay. So we're launching the kernel with 1 block and 5 threads, and we're passing in dev C, dev A, and dev B. Now, of course, dev C basically is empty. It doesn't have anything in it. But dev A and dev B has the information, right? So once this happens, the kernel is launched on the GPU. And on the GPU, we run this bad boy. right? So let's say this is, add kernel, right? Okay. So remember how I said on if this was normal C++ or CPU processing where it would do a for loop where it does I equals 1, then I equals 2, then I equals 3, then I equals 4, then I equals 5. Well, in CUDA world, in GPU world, this just runs one time with all 5 threads going through it simultaneously. So bang, 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 2, 4, 5, right? Simultaneously, real time, concurrent, parallel, any damn thing you want to call it, right? So these threads run one time and then you get your result, which is C, right? Because basically C would have been built with each of these threads. So let's call this thread 1, thread 2, thread 3, thread 4, and thread 5, right? So basically what it's saying is that all happening at the same time. For the first thread, this is 1, this is, thread 1. So C, the first integer in C is going to be A at 1 and B at 1, right? And basically it just processes it within this one thing. Then at the same time, the second one is doing the second thread, and the third one is doing the third thread, and the fourth one is doing the fourth thread, and the fifth one is doing the fifth thread, and it all happens one time. So with one push of a button, the entire array for C is built, right? And that's pretty much how it works. So where were we? So we push one block, 5 threads, and we have dev A and dev B, right? Which are basically these guys right here, right? So thread 1 basically adds 10 plus 11, right? Thread 2 adds 2 plus 22. Thread 3 adds 3 plus 30. Thread 4 adds 4 plus 44. And thread 5 adds 5 plus 50, which is 55, right? So each one of these bad boys basically represent a path through this thing, and it builds C all at the same time in real time simultaneously, right? So again, just to reiterate, we have our kernel, one block, five threads, and we basically push it through this guy and we get our result, right? Remember, these guys were passed in, A and B were passed in, and then we get C. So think of the thread as like a line of processing, right? But instead of it being, just one time, one after the other, instead of it being like this, it's like bang all at once, right? So that's what that is about. Now, where were we? Come on, guys. So when you're done with that, it's basically you're going to know what C is, right? So by the time you hit here, you are done with the CPU for the most part. You have used the CPU, you have done what you needed to do, and now you're back on the host. So you're on the host here, you call this function which runs on the GPU, and then you're back on the host by the time you hit here. Okay, so now remember I said the code is always checking for errors. Now it says check for errors launching the kernel. So CUDA get last error is I guess involved with figuring out if there's a problem launching the kernel. If there's a problem, tell me about it. Now CUDA device synchronize, basically what it's doing is saying CUDA device synchronize is saying wait for the kernel to finish. So don't process this until the kernel is finished, right? Now, why does it say waits for the kernel to finish? Why does it say that? The reason it says that is because when the processor is going through everything and then it launches the kernel, it doesn't necessarily wait for this to return or to be finished before it continues running other things. So while let's say this kernel was a process that took 15 minutes to finish, the host is going to launch the kernel. The GPU is going to be busy doing its thing, but all of this stuff is still being processed, right? So what this is saying, what this CUDA device synchronize is saying wait for the kernel to finish and return any errors encountered during the launch, right? So it's saying hold your horses, don't proceed until this guy is finished processing. So notice we didn't have to wait here because this only dealt with launching of the kernel. This deals with any errors happening, maybe like within the kernel, or CUDA synchronize return error after launching. See, it says after launching kernel. So this is involved with anything that happened after launching the kernel, and it tells you XYZ happened. Someone got drunk and had too much of a good time last night, and now there's a problem. So this is after the process. This is with launching the process. So this is one of the reasons why CUDA is so powerful, is that you could launch kernels and still process stuff on the CPU, and you could actually launch other kernels either on the same GPU that you have or on other GPUs. And that's sort of why the multiple GPU thing comes into play, because when you're dealing with high performance computing and you're trying to get stuff done and you want to get it done fast as possible, maybe you have 5 GPUs running at the same time, right? And you have to you need to get your stuff done. So it's not just going to launch one GPU or one kernel and stop. It's going to continue going. So that's what this is all about. Now, once you're done with the launch and everything is finalized and there are no errors, now you have to copy the data that was generated on the GPU back to the host. So remember how I said that we're pretty much done with the GPU? I said we're pretty much, which means that I guess you could consider this part to be involving the GPU, but it's trivial stuff. It's not anything major. All you're doing now, well, it's actually not. If the data is big, it's actually a big deal. But so CUDA status again, CUDA mem copy. So you're copying. This is the destination. This is the source. So we're saying copy the information in dev C, which is the result variable on the GPU, and put it back into the host C, variable C. And of course, again, we have to mention the size of the operation. And then we're doing CUDA mem copy device to host. Notice how the names are switched now. It's device to host. Before, it was host to device. because we're moving from the host to the device. But now we have our result and we're doing from the device to the host, right? So we're moving the data back to the host. And then, of course, error checking if there's an error. And we also, I don't know what this is about, but oh, I guess it's just saying, yeah, I guess it's just a label to go to here if anything were to happen. But anyway, don't worry about this. So this guy, after you use up memory and variables on the GPU, you have to free the memory again. You have to free, just like how where is it? No. Yeah, you have to free the memory. You don't want to allot memory to variables and then just keep the memory allotted on the device. You want to free it and say, okay, that memory allotment you could release and go back to do other useful and important stuff, right? And then you return CUDA status, which I guess is about error checking. So that right there sort of gets us to the end of Add with CUDA. So you see how much stuff this one line in main caused to get processed? A lot of stuff, right? So again, once this is finished, we're done with the GPU and we're done with calculating the results. And now we're simply printing it to our output, which is here. And we print it out, and yeah, and that's it. You have your result. Remember, in Add with CUDA, we had to take the information from the device and bring it back to the host, to the CPU, and then we have to reset. Reset must be called. So I guess good housekeeping again. CPU still doing housekeeping. You reset the CUDA device, and if there's an error, you fail, and then return 0. That's it. That's it. But I hope that this actually gives you some understanding of how so this gives you an idea of how this thing works. Please visit CUDAeducation.com. Support the cause, right here, support the cause, and like my video, subscribe to my channel, CUDA Education, on YouTube. What else is there? If you have any questions, I guess the best thing to do is just comment on the YouTube video, right? And that's about it. That's about it. I mean, this stuff is pretty cool. It's not too complicated. What the whole purpose of CUDA is, or why they developed it in this way, at least in the C++ implementation, is that, let's say way back several years ago, a complex and large program was written in C++, and now their graphics cards and they want to speed up the application using CUDA, right? NVIDIA tried to design CUDA in such a way where with one line of code, practically, right, they could just drop these kernels in the C++ code and have the application run 100 times faster because these kernels are doing all the heavy lifting, right? Because remember, the majority of this program, all the text here, majority of it is running on the host. It's running on the CPU. It's not running on the GPU. So with just dropping this one line of code, you could have your application run 1,000 times faster. So that's sort of the magic trick of why what they're trying to do here. They want to just put in a line of code, do a little housekeeping and basically be, have the application to be a ton, way faster. So that's the magic trick. Again, guys, remember to donate. It takes my time and energy and voice and recording, and it's not recording properly, and then having to re-record it again to get this stuff done. So help those that help you. Subscribe to my YouTube channel, CUDA Education. I'll try to post as much videos as I learn and understand how this game works. But good luck, and remember to comment if you have any questions, like the video, subscribe to my channel. I'm also on Twitter, but I haven't really been using it much. But yeah, maybe I'll get better at that. All right, guys, have a great day. Bye.